Because like you said, each code limited versus.
Right. Let's see, maybe as usual, maybe on what administrator check-in, fourth problem set was does do, fifth one is out, there's only 6 total, so you're like much of the way through the class. Is everything generally going all right? Everyone's like figured out how to like turn in, probably does on grade school, hopefully it was right. Yeah, that's all. It's like lots of argument game theory, everything going well generally.
Oh.
Potable water is in short supply. Cool. So we've spent a while now talking about auctions, and I'm gonna keep doing it for a little while. And in terms of how we've been doing it, right? Like we introduced the BCG mechanism, which is a very general technique for maximizing social welfare in all of the settings. And we beat up on it in a few ways. We said, well, only maximize social welfare, we characterizing all marker domains. We said, assumes you can solve the welfare maximization problem efficiently. So we thought about approximation algorithms, mechanism design, with last lecture with knapsack options. And what I want to do in this lecture is sort of like zoom in on a very particular objective that is very natural, that is not welfare, and see what we can do about it. Okay, well, oftentimes when you run an auction, although maybe like it's fine if you happen to do something with welfare maximizing, your sort of most direct objective might be things more like revenue. Like you're selling stuff, so you like to make. Okay, so I want to think in this lecture specifically about revenue. And even when you say that and then start to think about it for a little bit, the question is, what does that mean? Like, what does it mean to maximize revenue? What is the benchmark? In some sense, for welfare maximization, it's obvious what it means to maximize wealth. Like if I'm selling a single item and welfare is how happy you are with the outcome, then maximizing welfare corresponds to giving the item to the person who wants it the most. And more generally, we can talk about just the algorithmic problem given valuation functions of allocating items to maximize welfare. But what does it mean to maximize revenue? Maybe I get $10 for this, but maybe if I put it under your head, I could get $100 for this, or maybe if I kidnap you and hold you ransom and send a letter to your parents, I get $1 million for this. It's it's not clear what the benchmark is when you say maximizing. And so the first thing we're going to have to think about when we talk about revenue maximizing auctions is what is a reasonable benchmark to consider that will be able to actually compete. And this is in general a problem you can study in any kind of design setting. And often it's hard or not fully understood. What a revenue maximizing auction look like in very general settings. Right. So the VCG mechanism gave us an extremely general setting for welfare maximization. There's not a corresponding sort of general theory for revenue maximization. There's things known in different settings. And so what we're going to do is sort of spend today as sort of a case study thinking about maximizing revenue in single item auctions. And you could go through this case. You could go through this kind of approach in other settings, and sometimes it would work, and sometimes you would find that you hadn't encountered the 50-minute problem. Okay. So let's think about benchmarks for a moment. So the VCG mechanism was sort of remarkable in that it was welfare maximizing even ex post, by which I mean we didn't have to say okay, here's a distribution on bidder valuation functions and maximizing welfare somehow on average. We could really say in the worst case over what the actual end bidder would turn out to have as their valuation functions. On every single instance, point wise, we just find the welfare maximizing solution and we do it in a truthful. But for revenue, it's not so simple, and maybe just to give you some intuition for that, like, let's consider a single item auction in which there's only one bidder, right? It's hardly an auction at all if there's only one bidder. So let's think about it. So think about it for a moment. Yeah, it's sort of clear that like really the only truthful mechanism in like a single item auction, if there's only one bidder, is to just sell the item at a fixed price. It's hardly an auction. Like I'll just say like, here, this thing is like $5, take it or leave it. Okay, but like that is at least an example of a truthful auction, right? If my rule is you tell me if my rule is look, there's a price tag on this $5, you tell me your value, and if it's above $5, I will give this to you and charge you $5. If it's below $5, you don't get the item. It's clear that's a truthful mechanism, right? There's no reason to lie about your valuation. Like nothing you say is going to affect how much it costs. It's going to cost $5. You're just deciding whether or not to buy it. And if you think about it a little longer, maybe you could convince yourself that if there's only a single bidder, that's basically the only truthful mechanism. Okay, so like in some sense, if there's only one bidder, the design phase of a single item auction is deciding on like a price of the thing. And no matter what the price is, it's a dominant strategy. And the revenue is easy to think about. Like if your value is greater than the price, my revenue is equal to the price because you buy it at the $2. And if your revenue, if your value is less than the price, then you don't buy it, my revenue is 0. So like ex post, like after I know what your value is, like if I learn that you're a dongle collector and your value for this, a rare 2011 vintage dongle of this sort, if I learn that it turns out your value for this was $100, then like ex post, the optimal truthful auction for this item would have been to sell it for $100. Right? Like selling it for $100. If I set that price before I knew your value, that would have been a truthful auction. And after I learned that your value was $100, that would have been like the revenue maximum truthful auction. Like I could have gotten $100 for this if only I had set the price. But ex ante, like before I know your value, I don't know how to do that. Like I don't, right? Like if your value had ended up being $10, I should have set the price at $10. If your value had ended up being $1 million, the best truthful auction I suppose would have been the fixed price of $1 million. But like I can't set the price, like the auction is only truthful if I set the price independently of your value. I can't set the price at your value. I can't say, okay, first you tell me your value, then I will get out my price tag, gun and like just slap your value on here as a price tag. That wouldn't be a truthful auction. That would be a first price auction. We know that's not true. Okay, so like the problem is that like if I try to think about what the revenue maximizing auction is ex post, given that I already know the values, well, there always was some auction that if only I had like selected it like a priori, would have been the revenue maximizing auction. It just would have been the auction that sort of by lucky coincidence sold the item at the fixed price that happened to be exactly your value. But I had no way of knowing that ahead of time. And so like if this is how we defined our like revenue benchmark, we would find that, for a very simple reason, it was impossible to have truthful auctions that were competitive with the best revenue benchmark. Okay, does that make sense? This example makes sense that like any fixed pricing would give a truthful mechanism. Choosing the price to be your recorded bid would not give a truthful mechanism. But like after the fact, after I see what your values are, might think to myself, wow, there was a truthful mechanism that would have gotten me this maximum revenue of pricing it at your value, but like so the quantifiers are in the wrong order here. Right? Like there's no truthful mechanism I could have committed to ahead of time without knowing your value that would have achieved that. Is that clear? That's like the kind of thing we need to like worry about when we think about what our benchmark is going to be. And so there's different ways around this, and in later lectures we'll sort of think about other ways to deal with this problem. But one simple way is to say, okay, well maybe I don't know maybe I know some distributional information, like maybe I've never seen you before, but I've taught this class a bunch of times before. Every time I try to like sell this dongle, and every year, I get some bids. So I know some maybe distributional information about how much kind of students value, the 2011 line dongles. And so maybe like the way we would model that is, I don't know what your value is, but I'm sort of imagining that I know this distribution, probability distribution over values. And I'm going to assume that bidders have their value drawn IID from this known distribution. If I don't know the actual realization of bidder values, then I need to elicit if I need a truthful mechanism, but maybe I'll assume that I know what this distribution is. And the reason it's useful to make that assumption is now I can define a reasonable benchmark, which is I can say, look, given an auction format, I can ask, if I ran this auction, what would my expected revenue be in expectation over the realizations of the values drawn from the distribution? And I can start to ask questions like, well, what is the truthful auction that maximizes expected revenue? Okay, so once I have a distribution, before I see the bids, I can talk about what the expected revenue of an auction is, and then I can evaluate the expected revenue of an auction independently of what the actual bids are. And then I can ask for the best auction that I want to maximize for. Okay, so just to like go through an example of that kind of reasoning, let's think about this single item, single bidder auction, where the only thing I can do is decide on a fixed price for this good I'm selling. Well, in that case, it's sort of easy to think about what is my expected revenue for selling the item as a function of the price that I sell. Okay, so what's going to happen? If I set price P, then I'm going to make P dollars exactly when the buyer's valuation is above P, exactly when they're worth it to buy this for P dollars. And when their valuation is below P, I won't make any dollars. They won't buy the item. And so if I write f of P for the cumulative distribution function for my distribution D, by which I just mean the probability that a bidder whose value is drawn from this distribution is less than P, the probability that they are not willing to buy the item at price P, then my expected revenue, if I price it at P, well, the P, that's how much money I get if they buy the item, times the probability they buy the item. That's just probability that their valuation is greater than P, which is just 1 minus N. Right, so it's like I can just write down an expression for the revenue. Right, just like P, the probability that they buy the item, times the probability that they buy the item, the probability their value is greater than the price. And if I know what the distribution is, I can then just like solve an optimization problem and find the price that so for example, if I sort of believe that your value for this item is like uniformly random between 0 and 1, well, then the probability that your value is less than the price is equal to exactly the price, right? Everyone's value is less than 1, nobody's value is less than 0, half the people have value less than half. So this function f of P is just P. In which case I can compute, well, like the revenue I get for pricing the item at P, if your value is drawn from the uniform distribution, it's just P times 1 minus P, and I can like try to maximize that and find that it's maximized if I price my item at 50 cents, at half a dollar. Okay, and then in expectation I make 25 cents, quarter of a dollar, and there's no way I could have done better in expectation. I priced it either higher or lower, I would have made less money. And so here, at least there's like a well-defined price that maximizes revenue amongst all prices. Okay? In expectation of the distribution. Does this make sense? Like the maneuver here, the sort of change from how we've talked about things in past lectures is now, although we're still going to want the mechanisms we designed to be like dominant strategy truthful, which is like a worst case notion. Like, this distribution is sort of has no relation to the incentive properties we want. Like we still want it to be a good idea for you to tell the truth no matter what other people report. By sort of assuming that there's a distribution over bidder values, this allows us to evaluate, like ask the question, what is the expected revenue my option is going to get? I can ask that question before I see the bidder values. And so it makes sense to ask then the question, what is the option format that maximizes expected revenue? Okay, so in order to even ask that question, we had to figure out what our benchmark is, and that's sort of the role of the distribution. Does that make sense? Okay. So, okay, so we just, like we handled the case of one item and one bidder, it was just optimizing over a single price, so write out the expression and solve. Let's now try to handle one item and many bidders. Okay, so, a little bit for one item, many of you might admit, the BCP mechanism in this case, remember, will just give the item to the person who bids the highest and ask them to pay the second highest price. That'll maximize welfare. It'll always, it's a truthful mechanism. It'll give the item to the person who has highest valuation, but it won't necessarily maximize that. Okay, so what do we mean to maximize revenue? Just sort of writing down our problem, given this new way we have of defining like a benchmark. Like a truthful mechanism, remember it's going to have two parts. It's going to have an allocation rule X, and defined as a function of the bids, who gets the item. And it's going to have a payment rule P that's going to define as a function of the bids, how much they pay. And what we want to do is maximize expected revenue, which is just, well, what's revenue? Is the sum over all of the bidders, so the amount of money they pay us. And it's the expected revenue, so it's the expectation over what their valuations might be when their valuations are each drawn IID from this distribution. Okay. And this is a single parameter domain. And so we know over it's only a single item, your value is likely to be if you win it, it's zero otherwise. So it's a single parameter domain. And so I know from our sort of characterization theorem that like, if this is going to be a truthful mechanism, X needs to be monotone non-decreasing. You have to be only more likely to win the item if you raise your bid. And we even know in that case what P needs to look like. Okay, well, like it's not like a mystery, even like X has to be monotone non-decreasing, and like P needs to look like this. And so, like in principle, there's like a well-defined optimization problem here. Okay, like find the pair XP such that we want to maximize the expectation of the sum of this expression, summed over all I, the expectation when the values are drawn from this distribution. And we'd like to do it subject to the constraint that X is a monotone non-decreasing function because that's what we need for dominant strategy. Okay, does that make sense? But like, this might sound like a hairy optimization problem, not clear how to solve it, but like at least at this point, like a well-defined optimization problem, right? It's like we're optimizing over the space of mechanisms XP that are like dominant strategy truthful, but since this is a single parameter domain, we know exactly what that space looks like. It's a set of all X's that satisfy the monotone non-decreasing property paired with P's that are exactly equal to this expression that comes out of our characterization theorem for single parameter domain. Okay, and among that set, among this sort of set of XP pairs, we would like to find the one that maximizes the expected sum of payments made to us, subject in expectation over the values from. Okay, yeah.
With the expectation, but you're not getting are you getting a payment from everybody regardless of whether or not they win? Or
Well, it depends what the payment rule looks like. For lots of natural auctions, like first and second price auctions, the payment is zero for people who don't win.
oh, so it just keeps the general, like that's just a rule, not necessarily.
Well, this is how we would write it even for, like a second price auction where the person who wins pays the second price and everyone else pays zero, because we don't know who's gonna win, right? Like this is the expectation over what the bids are. So depending on what the bids are, like might win. And so, well, like the thing we want to do is maximize the sum of the payments we receive. Now, it might be that after we see the bids, only one person ends up paying us. But we have to still, I can't just say maximize the payment of like bidder 5, because I don't know that bidder 5, I don't know ahead of time that bidder 5 can people. So I want to maximize the sum of the payments, although it might well be that people who lose the item pay 0. Does that make sense? Okay, so is it clear that it's not at all clear how to solve this problem yet, but is it clear at least that we've now asked the question in a way that there's a well-defined answer among the set of all dominant strategy truthful mechanisms for which we have a good characterization, right? It's allocation and payment rules such that X is monotone non-decreasing and the payment looks like this. That's from our single parameter domain lecture. We would like to find the mechanism that maximizes this expression. But it's now like we started from like a mechanism design problem, but like now it's a well-defined problem, right? Like, find a pair XP satisfying a known constraint, maximizing a known effect. Okay, that makes sense. Like, now if you're like good at calculus, you can forget about like mechanism design. Let's like try to solve this problem. Okay. So like you might think to yourself, okay, maybe I'm pretty good at calculus, but this problem is kind of annoying because it's like a constraint optimization problem. But if you just said, okay, like PI of V is equal to this expression, I'm just maximizing, this expression where the variables are now just like xi of V potentially. And then maybe you run the calculus crank and you optimize for that. But it's not an unconstrained optimization problem. We can't set the variables xi of V in any old way. They're constrained that they need to be monotone non-decreasing. So that's gonna like make the problem like more complicated. But let's forget about that for now. Like let's sort of just like assume that X is monotone for now. Use our expression for P to derive the optimal X. That doesn't really make sense because we're deriving X under the assumption that X is monotone, but like X isn't something that was fixed, like we're deriving it. But like let's just like ignore that for now, and like maybe we're lucky, right? Like it might be that we solve this unconstrained optimization problem. We say, look, let's just maximize the sum of the payment. Let's find the X that maximizes the sum of the payments without any constraint at all. And like if we're super lucky that the world is a good place, then maybe when we solve that optimization problem, what will pop out of it is an X that is monotone. In which case we're done, because if the solution to the unconstrained optimization problem already gives us a monotone allocation rule, then certainly adding the constraint that the allocation rule is monotone won't change. Okay, does that make sense? Like we have this hard problem, so we're just gonna like hope that God loves us and ignore the part of the problem that makes it like hard and all that, and hope that like in the end everything works out. Does that make sense? That's your strategy? Okay. So yeah, so that's gonna be our plan. Right, so let's just like bite the bullet and try to do it. We'd like to find the X, right, the allocation rule that maximizes our expected revenue. Remembering that we have an expression for what the payments are, the expected monotone, in terms of the allocation. The allocation rule, the thing X, really is the only decision variable. And this is an expectation really over like n numbers, the values for each of the n bidders. But the expression we have for the payment rule is really sort of from the perspective of bidder I. like what does bidder I need to pay as a function of his bid and everyone else's bids. And so maybe like the thing we should do is to sort of start by breaking up the expectation across the different bidders. Okay, so like first of all, expectations are linear. So I have an expectation of a sum, but that's the same thing as a sum of expectations. Okay, so let's take the sum on the outside. We're going to sum up over all of the bidders and think about the expected revenue of that bidder, the expected payment made by that bidder. And that's that's sort of like an expectation over the bid of that bidder I, the value of that bidder I, and the values of all of the other bidders. They're drawn independently of one another by assumption. So let's just, instead of writing the expectation over, all n of the values at the same time, let's first take the expectation over, everyone else's value, everyone other than bidder I. Then inside there, we'll take the expectation of bidder I's value. And then, once we have a value for BI and for B minus I, we just have some like complicated expression for the payment rule that we can plug in. Okay, we want to like maximize this thing. Nothing's happened yet. We just wrote down expected revenue. We brought the expectation in the sum and we sort of separated out part of the expectation that relates to values for people other than bidder I and bidder I. And maybe just a little bit of notation. We've got this distribution D, right? And we've already given notation for the probability for the cumulative distribution function for D. That was just the probability that the bid drawn from this distribution is like less than some price. It's also going to be useful for us to have notation for the probability density, which if it was a discrete distribution, would just be like for every possible value p, what is the probability that you have value exactly p? Okay, and so in particular, if f of p is like the probability density, probability that you have value p, then little f of p. Then this thing we already talked about, the cumulative distribution function, big F of p, which is just the probability that your value is less than p. Well, that's just the integral from 0 to p of f of p. Okay, or just for a discrete distribution, that's the saying, look, the probability that you value this at less than $100 is just the probability you value it, assuming you have dollar valuations. The probability you value it at $1, plus the probability you value it at $2, plus the probability you value it at $3, all the way up to $100. Okay, so like little f of p, think of that as the probability that this item is worth exactly $p to you. Big F of p, that's the probability that this item is worth less than $p. Okay. Okay. And so, we're maximizing the sum of these payments. If we could sort of maximize this expression term by term, that would be great. And so maybe let's just zoom in on this sort of final term here. Okay, like in this final term, you have been given an identity, you're bidder I. Okay, put yourself in the role of bidder I. The value of all of the other bidders have already been fixed. Okay, so the only thing we don't know is your own value, BI, that's drawn from this distribution. And I'd like to find the payment rule that maximizes your expected payment given this distribution over your own value. Okay, so I want to zoom in on that inner term. Okay, so just everyone else's value is fixed. We're just looking at for bidder I, what is the expected payments made by bidder I, given that everyone else's value is fixed, and we're just taking the randomness for bidder I's value. Okay. Now we know what the payments made by bidder I has to be in terms of the allocation rule. If this is going to be a dominant strategy for mechanism. This was the main theorem we proved in the single parameter domain lecture. And if X is a monotone allocation rule, then the payment rule that makes it truthful has to look like this. It's just your value times the allocation rule when you bid your value, minus the integral from the integral over all of the bids less than or equal to your value, from 0 up to your value of your bid, of what the allocation rule would have said had you bid this lesser value. Okay, you don't really have to remember that, it's just, like reading off of the slide for the theorem we proved 2 lectures. Okay, so I'm just plugging in, the point is just this quantity Pi of V, the amount of money you have to pay if you bid V, that's not some unknown thing anymore. That's something we can write down in terms of only the allocation. Okay, so the point is, this is an optimization problem that I can think about in terms of just the allocation. Payment rule is fixed once I fix the allocation. Okay, and this is like a difference of 2 things, right? And expectations are linear over sums and differences. So I can think of this as like the difference between 2 expectations. On the one hand, I have the expectation of VI, your bid, times the allocation that you get when you bid VI. Okay, this will be like, 1 or 0. Did you win the item or not? And then separately, there's the expectation over like the sort of negative part of the payment rule, which is just the integral over all of the smaller bids Z you could have considered making of the allocation rule that would have resulted, the allocation that would have resulted when you bid C. Again, remember this xi is going to be like 0 or 1. Do you win the item or not? At that bid C. Okay. And we kind of know what expectations look like, right? If I have like a discrete distribution, if there's like 10 different things that can happen, and I've got say 6 things that can happen. So I don't need an exotic die, but I've got a regular 6-sided die, and I roll it, and there's some amount of money you're going to pay me for each possible outcome. Well, what was the expected amount of money I get? Well, it's the probability that I roll a 1 times the payment I get when I roll a 1 plus the probability I roll a 2 times the payment I get when I roll 2, right? So it's the sum over all the possible outcomes of the probability of that outcome times the value I get when that outcome is realized. And it doesn't have to be discrete. If it was continuous, I would just replace all of those sums with integrals. Okay. So what does it mean? The expectation of my bid VI times my allocation XI when I bid VI. Well, that's just the integral over all possible values I might have between 0 and 1, assuming values live between 0 and 1, of the probability that my value is VI. Okay, well, that's just f of VI, that's the probability density of VI, times the value of the thing I'm taking the expectation over when my value is VI. So times VI times the allocation when I bid VI. Okay, so this is just the quantity inside the expectation, but now I'm taking the integral over all possible values for my value VI, weighted by the probability that I draw that value. I just expanded out the definition of the expectation. And I can do the same thing here, right? This is also an expectation over VI. And so I can have this thing, I'm taking the expectation over this integral from 0 to VI of, the allocation I would get when I bid something lower, Z. And it's the expectation over VI, so I just integrate over all possible values that my VI might take, 0 to 1, and I weight them by the probability to have that value at the VI. This is just expanding out the definition of an expectation. Okay, no funny business yet. Just expanding out definition. Okay. Now, whenever like the first rule of like mathematics is when you have 2 nested sums, you should like interchange. Right? Like if you got it, you got to do it. And the second rule of mathematics is when you've got two nested integrals, okay, but now maybe you need to like look up some technical conditions to see if you can do it, but usually the answer is yes. And then, you know, if you can, you go for it. Like, okay, so like here we are, we've got like, you know, two nested integrals here. Like we've got an interchange. So let's do it. So no funny business for the first part. Like this first term, I'm just not touching it. Okay. And like before, like on the outside, I was integrating over VI, and on the inside, I was integrating over Z. Okay, VI was integrated from 0 to 1, Z was integrated from 0 to VI. Now I'd like to do it in the opposite order. On the outside, I'm going to integrate over Z, and on the inside, I'm going to integrate over VI. And I just have to be like, do bookkeeping to keep track of like the bounds of integration. So like, what is the range of Z? That's what I should integrate over here. Well, Z was going to be anything less than your bid, VI. And your bid can range anywhere from 0 to 1. So Z can also range anywhere from 0 to 1. Right? Like there are portions of this integral where Z takes any value anywhere from 0 to 1, because Z ranges from 0 to VI, but VI ranges all the way up to 1. So my integral over Z had better now be from 0 to 1. And well, once I fix Z, I fix this term here, xi of Z and v minus I. And now I have to figure out what my bounds of integration are over VI. Now, before VI was ranging from 0 to 1, and Z was ranging from 0 to VI. So now, like, my VI should range from Z to 1. And maybe just to like, I never understand integrals. I always have to like pretend they're sums. Like things make sense in discrete math, but they're sums, right? So it's like, why is this the right thing to do? Well, you know, like, how many times do I encounter the term xi of z v minus I multiplied by f of vi? Right? Let's just pick a value. Vi is like 1/2. Right? So how many? How many times do I encounter the term xi of 1/2 v minus I? Well, I encounter that for every value of vi that is bigger than 1/2, right? Because here I'm integrating from 0 to vi. So if I'm integrating from 0 to something less than 1/2, I never encounter v equals 1/2. But for every vi that's bigger than 1/2, I encounter. So to sort of get the same set of terms to match up, for every z, xi of z times v minus I, well, I would have encountered that for every value of vi that was bigger than z. So in order to make sure I have the same integral, I have to integrate from z to 1. Okay, there's some bookkeeping that you can sort of maybe verify at home to make sure I don't have any business here either. But I just sort of interchanged the integrals. You have to do the bookkeeping to make sure the bounds of integration are correct. And if you're like me, you just pretend there's the way to like figure out what the right answer is to like pretend there's sums, in which case this would be like a combinatorial problem that like human brains can think about, in which case you can figure it out and then like you cross your fingers and hopefully it's good variables. And it is. Okay. So that was sort of the main piece of funny business, the sort of interchanging these integrals, which obviously you can always do when you have the opportunity to. And now I'm just going to do some like syntactic funny business. So like the names of variables that you're summing over or integrating over don't matter, right? Like I could say the sum from I equals 1 to n of 1 over I squared. That would be something. Or I could say like the sum from like j equals 1 to n of 1 over j squared. Or I could say the sum of capital letters 2, z equals 1 to n, 1 over z squared. Those are all the same thing, right? It doesn't matter the name I give the variable that I'm integrating. So as it happens, like in this outer integral, I've called the variable z. And in this inner integral, I've called the variable vi. But like it could have been that in this outer integral, I just chose like a different name. Picking one at random, maybe I called this variable vi. Maybe I named this variable z on the inside. I could swap the names of those variables, and I wouldn't have changed it. Okay, so that's all I'm gonna do. I'm gonna, wherever I previously wrote z, I'm gonna write vi. And wherever I previously wrote vi, I'm gonna write z. And that's fine. It might seem a little suspicious because I used variables that, like I didn't pick, like, if I had called this z prime and vi prime, you wouldn't be at all suspicious. Maybe you're a little suspicious if I've used names that I was using before, but well, like I've just changed the names of the variables. So like it's definitely the same expression, right? The name of the variable I'm integrating over that. Okay. And that's really the last piece of funny business. And now, I've got an integral over like terms that I can kind of combine, right? Like here I've got an integral over vi, here I've got an integral over vi. I can combine them into the same integral. Right, so maybe I think of this as just right, so let's maybe just simplify things. Right, so okay, the simplification I just described is going to happen in 2 lines, not in 1 line. Forget that. Let's just simplify this now. What is this? Remember, f of z is like the probability that your value is z. Okay, so integrating over all values you might have from vi to 1, that's just the probability that your value is bigger than z. Okay. This thing is just the probability your value is bigger than vi. And we have a name for that, right? But like the cumulative density function, capital F function, was telling you what was the probability that your value is less than something. But 1 minus that is just the probability your value is greater than something. And so this integral here, right, we have a name for it. Instead of writing the integral from vi to 1 of f of z, I can just write, well, like the probability that your value is bigger than vi, which is just 1 minus f of vi. It's 1 minus the probability your value is less than vi. Okay. That's all that happens between this line and this line. We just like notice that we have a name for this probability that you value the item more than vi. Okay, and then like here's where we notice that like what we have is 2 integrals that are both integrating over the same variable. They're both integrating over your value vi. And so let's just combine them. Okay, like here, we're just multiplying vi times the allocation rule when you did vi times f of vi. Okay, so that's just vi times the allocation when you did vi times f of vi. And we're subtracting off from that this other term, this other expression of vi, which I can write as again the allocation that you get when you bid vi times 1 minus the cumulative density at vi times the probability that you value the item more than vi. Okay. And if I'm going to multiply by, if I'm multiplying by f of vi, the probability you value the item exactly vi dollars out here, and I don't want to see the expression in my second integral, I have to divide by it. So I'm just combining, it's like the sum from, 0 to the maximum value you might have of something, minus the sum from 0 to the maximum value you might have of something else. We're just combining those into the same sum. It's like the sum from 0 to the maximum value you might have of like something minus something else. Okay, just simplifying, that's all that happens. Okay. And then we might just look at this and notice that this is an expectation. Right, what is it? It's an integral from 0 to 1. It's an integral over all of the values you might have for the item of something weighted by the probability that you have that value for the item. That's an expectation. So just like we sort of took the definition of expectation up here and unwrapped it into an integral, here we're doing the reverse. We have an integral, we notice it's actually like describing an expectation. Let's wrap it back up into an expectation. So just noticing that like this integral here is just the expectation over your own value drawn from this distribution of this funny expression. Your value minus the probability your value is larger, divided by the probability that you have exactly that value times your allocation when you did that value. Okay, so it's not a funny expression, but it's just an expectation. Okay. So you know, like this was some like long derivation that involves like integrals. So when I ask, does this make sense? I don't mean like, can you recover all of these steps? You know, like if I like take the slide away, I just mean like, did things vaguely seem like they were making sense along the way? Like nothing crazy happened here. We just did like a calculation where we like started by writing out what the payment rule was. We noticed that we can turn expectations into integrals. We noticed there's like simple algebraic manipulations we can do to integrals, and in the end, we ended up noticing that like your expected payments can be written as a much simpler expectation over your value. Yeah. Yeah, Z is like just the name of the variable we're integrating over here. But like, yeah, think about it as, you know, if you bid VI, then Z ranges from 0 to VI. So it's like all of the bids you could have made less than the one you actually made. And it's like, and you know, and then like this is the indicator of whether you would have won the item had you bid Z for each Z less than your true value. Yeah.
And was there an interpretation for the first slide that you teach?
Yeah, so this comes from like the characterization from a few lectures ago. And if you sort of remember, I don't know if there was like a great interpretation, but like we worked out, for example, that in a single item auction, this recovers or rather, sorry, we noticed that if we plug in the allocation rule for the VCP mechanism, give the item to the person who values it the most, then this payment rule just reduces to like the second price. This is a generalization of a second price auction, right? Because like the integral over all of the lower bids, all of the bids you could have made that were smaller than your own, of the indicator of whether you won or not. Well, you would have won at every lower bid that was higher than the second largest value. And so for a second price auction for the winner, this just corresponds to your value for the item minus your value for the item minus your value for the item minus the second highest bid for the item, which was the second price auction. And so this was some generalization of the second price auction rule that works for arbitrary single parameter domains. Okay, so long, painful derivations, lots of squiggly lines, but in the end, like the thing we want to maximize is some like expectation. Okay. And so like we can make it even sort of simpler, right? If we sort of notice that like, okay, like this is just the allocation. This is just like the indicator 1 or 0 of does bidder I win the item when they bid VI. This thing is some funny expression, but it depends only on VI. It depends only on bidder I's valuation. It doesn't depend on like the bids, for example, of the other bidders. So like if we just give this thing a name, this is some transformation of bidderized valuation, right? Just turn the valuation, this other number. Then like the thing that I want to maximize revenue, it's like especially simple. Right? It's just the indicator of does bidder I win the item times this number, which is a function of bidderized value. Okay. Let's give a name for this money expression. Let's call that the virtual value. And we started out wanting to maximize revenue. But we've gotten to a place that looks a whole lot like maximizing welfare. Right? What's maximizing welfare? Well, it's giving it to the item, giving the item to the person who has the highest value. That's the welfare maximization. So this is the welfare maximization problem. It's just with values replaced with virtual values. How do I maximize this? Well, if it's a single item auction, I can only give the item to one person. The max of B is going to be like 1 for the winner, 0 for everyone else. So how do I maximize this? Well, I give the item to the person who has the largest virtual value. Well, not quite, because the virtual values don't have to be positive numbers. Right? What's the virtual value? It's your value for the item like minus something, it depends on the distribution. So the virtual values could be negative. So I don't actually necessarily want to give the item to the person who has the highest virtual value. I want to give the item to the person who has the highest virtual value if it's positive. And if everyone's virtual value is negative, then I would like to not give the item out at all, not allocate the item. Right? Because if I gave the item to someone with negative virtual value, this expression would take on a negative value. But if I just didn't allocate it to anybody, if X of E was 0 for all bidders, then the expression would just be 0. Okay. So once the problem looks like this, the optimal option sort of is obvious. Like this is what I want to maximize. I should, like give the item to the person whose virtual value, this thing is the largest, assuming that's a positive number. And otherwise I should not give it to anybody. And remember, there was like this caveat, this whole derivation started from the presumption that this was the payment rule that made our auction truthful. And this was the payment rule that made our auction truthful if X was monotone. Of course, if X was not monotone, then you can't make it truthful. And so this whole derivation is like only valid if X is monotone. But now that we know what the optimal allocation rule looks like, it just like gives the item to the person who has the largest virtual value to make it positive. Well, the allocation rule will be monotone so long as the virtual value is monotone. As long as if this expression is monotone, if raising your bid only increases your virtual value, then the allocation rule is going to be monotone too. We're just giving the item to the person who has the largest virtual value. And so let's say that a distribution is regular if this thing is monotone. The virtual value function is monotone, we'll just say the distribution is regular. And therefore, we will immediately have that for any regular distribution, the revenue maximizing option is monotone. Sort of by fiat, we just regular just means the thing we need to be monotone is monotone. But I would just note that lots of things are regular. And so checking that the uniform distribution is regular, you get, look, for the uniform distribution, the probability density is 1 everywhere. The cumulative density at VI is just VI. And so we just get that the virtual value is VI times 1 minus VI, which is just 2VI minus 1, and it's increasing. And notice, what does this allocation rule say you should do if there's only one bidder? Well, it's only one bidder. Then it's clear who's going to be the highest bidder. It's you. You're the only bidder. But it's still not clear if I should give you the item. Right? I only give you the item if your virtual value is positive. So I'll give you the item exactly when your virtual value is positive, which is sort of like saying that I'm going to charge you a fixed price, which is equal to the smallest or equal to the smallest bid you could make such that your virtual value would still be non-negative. The inverse of the virtual value function is 0. And just looking at the uniform distribution again, your virtual value is just 2vi minus 1. Well, this is equal to 0 at exactly 1/2. The smallest bid you could make such that I would still give you the item is 1/2. That means that this thing we derived for maximizing revenue in multi bidder auctions. In the single bidder auction, it recovers this simple calculation we did at the beginning of the lecture. Because I should charge you a fixed price, and the fixed price I should charge you is 1/2. And that was the calculation we did at the very beginning of the lecture. So if I'm just selling you a single item and your value is uniformly random between 0 and 1, then I should charge you 50 cents. That's going to be the revenue maximizing price. And we did this like complicated thing. We took all these integrals, we did all this stuff, and we got a general auction format now. I compute everyone's virtual value, which is just some transformation of their bid, and give it to the item, give the item to the person with the highest virtual value, assuming it's non-negative. But just as like a sanity check, to make sure we didn't confuse ourselves with all of this complicated stuff and lose track of the real problem, like it is consistent with what we calculated at the beginning. If there's just one bidder, their value is uniform between 0 and 1, the revenue maximizing price is 1/2. That comes directly out of this expression because to figure out the revenue maximizing price for like a single bidder, all we need to do is figure out the value that makes the virtual value function equal to 0. That's the threshold at which the allocation shifts from you not getting the item to you getting the item. Okay, does that make sense?
So for the form of the virtual value, is there any intuition for why it came out to look like that?
Yeah, I don't know. There's a great intuition. I mean, like, you know, sometimes that's what comes out of, like this calculation. This is called the hazard rate, or maybe the inverse hazard rates. So like places where this expression comes up, it's like, how long is your light bulb gonna last before it burns out? Well, there's some distribution. And so I can start asking, okay, well, maybe your LED light bulb, like on average it lasts, 5 years. Your particular light bulb, it's lasted 3 years already. Like how long do you expect it to last from this point forward? Maybe it lasts, maybe on average it lasts 5 years. Yours has already lasted 6 years. How long do you expect it to last? So you calculate and it's for light bulbs. If you're like selling life insurance, you might ask questions like, what's the chance you're going to go on living for another year, given that you're already 7? Okay, so that's called the hazard rate. And so, like the inverse of this is like, what's the probability you're going to live to, VI years of age? Given that you've already lived at least VI years, what's the probability you're going to die this year? Okay, so this is the inverse hazard rate. So the condition we want is that the hazard rate should be sort of like monotone increasing. Like the chance you're going to die this year should only go up as you get older and older. Any distribution that has that property, you can maximize revenue. So that's maybe intuition about the meaning of this quantity, although not why it goes up here. Okay, but yeah, like if your light bulb is only becomes more likely to burn out today, the longer it's gone out, then it's the kind of distribution that for which this allocation will define. And that's true for many distributions. Okay, does that
Yes.
sort of answer your question? Okay.
Thank you.
Good. And so, okay, so this was like some complicated thing. But like you can ask, okay, like what does this complicated thing like actually look like? Right? It's like, okay, so we're giving the item to the bidder who has the largest virtual valuation when that virtual valuation is positive, otherwise we're not giving it to anybody. And so because, for these regular distributions, the virtual value function is monotone. Well, giving it to the person who has the largest virtual valuation is the same as giving it to the person who has the largest valuation. The allocation rule is actually a lot like for the VCG mechanism, a single item auction. We're just going to give it to the person who reported the highest value. Very natural thing to do. Now, what does the winner pay? Well, we know what the payment rule is. So say you're the winner. You bid VI star, what do you pay? Well, you pay VI star minus the integral over all of the lower bids you could have made, lower than VI star, of the indicator for whether you would have won. Okay, so at what point would you win? Right, so it's the integral of the indicator that you win for all bids that would cause you to win, and higher, for P star is the lowest bid that would have caused you to win. So what's the lowest bid that would have caused you to win? Well, if I were just giving it to the bidder that had the highest value, like I do in the VCG mechanism, the lowest bid that would have caused you to win is the second highest bid. That's why we would have recovered the second price. But here, you could have bid more than the second highest bid and still lost the auction. How? Well, if you had bid lower than the second highest bid, if you had bid higher than the second highest bid, say you get the high bidder. But if your virtual value was negative, then you still would have lost the auction. I wouldn't have given the item to anybody. And so the lowest bid that would have caused you to win, which is the amount of money you need to pay, is whichever is larger. Either the second highest bid or the bid that would have caused you to have virtual value 0. Either of those things might be the threshold. So now instead of asking you to pay the second highest bid, I'm asking you to pay whichever is larger, the second highest bid or some other number that is a function only of the distribution bids withdrawn. And so this is just like a second price auction with a reserve price. Like saying, okay, I'm going to sell this. I'm going to set a reserve price of $50, which means I'll sell it to the highest bidder if the highest bidder bids more than $50. Otherwise, nobody gets it. And the amount of money you have to pay, if you're the high bidder and you bid more than $50, is whichever of the following two things is larger, the second highest bid or $50. Okay, that's the form of the revenue optimal auction. That's the auction in which I give it to the second price auction with a reserve price. That's the kind of thing you see on eBay. Okay, so we did all of this math, and we were optimizing over a potentially complicated space, right? Like arbitrary monotone x's. And yet the thing we derived in the end was a pretty simple kind of auction. It was like the thing that's run on eBay. It's give it to the highest bidder at what price? Well, give it to the highest bidder if their bid is above the reserve price. At what price? Well, the lowest bid that would have still allowed them to win, which is the higher of the second highest bid or the reserve price. Okay, so it's the same as the VCG auction, except there's this reserve price. If none of the bids clear the reserve price, you don't sell the item. Okay. We derived this all, under the assumption that C was regular. We needed the allocation rule to be monotone, not decreasing. You can do some more math and make it work, even when D is not regular. No big deal. We took these expectations and we sort of took advantage of linearity of expectations. So it was kind of important that the values were drawn independent. This wouldn't work anymore if my value was correlated with your value. But nothing in this derivation actually needed all of our values to have the same distribution. So this would have worked if I had a different belief, a different distribution for each of the bidders. Maybe there's different kinds of bidders. Maybe some bidders, you know, they like walk in like a tuxedo and a top hat, a monocle and a pocket chain. I sort of expect that they might be willing to pay more. But, okay, so I could have a different prior distribution for them than for other bidders. What this would mean is just that everyone now has their own virtual value function. Virtual value function is a function of the distribution, which I believe your values are your own. Everything would still make sense, except the auction would no longer be quite so natural looking. Right, because I always give it to the person with the highest virtual value, but if different people's virtual value functions are different from one another, this no longer necessarily means I give it to the highest bidder. Sometimes someone who's not the highest bidder, but who has a surprisingly large bid, which causes them to have a very high virtual value, would be the winner. Okay, it would still be the revenue off the auction, but it would no longer be this sort of simple eBay style auction. We really crucially used the single parameter domain structure, like we used like this characterization we proved specifically for single parameter domains. And it doesn't extend beyond single parameter domains, and more generally, when you start asking questions like, what is the revenue optimal auction in some complicated setting, you'll get to questions we don't know the answer to. It requires knowledge of what this prior distribution is at the reserve price. How would you know that? We'll sort of think about that over the course of the next few lectures. And let me just sort of prove one more mini result for you. So we now know how to maximize welfare, quite generally with the VCP mechanism, and in particular with single item auctions on a second price auction. We also know how to maximize revenue. It's a second price auction with a reserve price, which is definitely not welfare maximizing, because I'm giving up on welfare every time I decide not to allocate the item. So it's like, are these things like really in conflict with one another? Like, if we care about revenue, we have to give up on welfare and vice versa. And it sort of seems like we might, because again, think about selling to just a single bidder. Okay. What would the victory auction do? Well, it's a second price auction, but if there's only one bidder, the second price is always zero. So the victory auction would always allocate the item. It would like give the item to you as it must to maximize welfare. If there's only one person, you have to give the item to that person to maximize welfare. And if I'm going to give the item to that person, no matter what they bid, the only way I can have a truthful auction is if I don't charge them. So the victory auction, like if there's only a single bidder, like totally gives up on revenue. It's like gives the item away for free. And yet we know, like, if their value was drawn uniformly from 0 to 1, for example, we don't have to get 0 revenue. Like I could have just like priced the item at 1/2. I wouldn't have maximized welfare. I'd only give the item out at the time, but I would get some revenue. I'd get like revenue a quarter, like an infinite, factor more than like the 0 revenue of the VCP mechanism. So it seems from this example that maybe like there's no way to like, somehow simultaneously think about optimizing revenue. But you can think like, okay, well, fine, if there's one bidder. But what if I have two bidders and they both have values that are drawn uniformly between 0 and 1. And suppose I run the welfare maximizing option, VCP mechanism. Well, now I won't make 0 money. I'll give it to the highest bidder and I'll collect the value of the second highest bid. And so I could ask, what's my revenue for running the VCP auction if I have two bidders? Well, that's just the expectation of the smaller of two draws from the uniform distribution. And it's, you can work out what that is. It's a third. So it's bigger than a quarter. If I run the welfare maximizing auction with two bidders, I actually make more money than if I run the revenue optimal auction with one bidder. So like, if I have to like allocate my time to like setting the optimal reserve price or like recruiting one more bidder to join my auction, then like even from the perspective of revenue, I'm better off using my efforts to recruit one more bidder to put my more. And that's true in general. So imagine we have a single item auction in this setting we've been studying, where everyone's value is drawn I out of E from some distribution D. The claim is for any number of bidders n. If I think about the amount of money I make if I run the revenue optimal auction we just derived in the setting in which there are n bidders, I actually make even more money if I run the victory auction, the welfare optimal auction, in a setting with only one more bidder, n plus one bidders. So it is true in general that even if I care about revenue, not welfare, I'm better off in terms of revenue running a welfare optimizing auction with just one more bidder. So if I'm faced with a choice of how to spend a week's worth of time either trying to compute the optimal reserve price or recruit one more participant in my auction, I should just recruit one more participant. So why is this true? So let's do a thought experiment. Here's a hypothetical auction for when there's n plus one bidders. Okay. It's sort of a dumb auction. I'm going to partition off the first n bidders, then I'll have bidder n plus one off to the side here. And I'm just going to run the revenue optimal auction for the first n bidders, the thing we just derived. So the second price auction of a reserve. Yeah, so the revenue optimal auction for the first n bidders. Maybe one of those bidders wins the item, but maybe nobody does. Nobody bids above the reserve price. If nobody bids above the reserve price, if the auction fails to allocate the item, I'm just going to give the item to this bidder off to the side, bidder n plus one for free. Okay. So it's a silly auction, so I'm not really going to really run it, but let's think about it. Okay. So a couple of observations. The revenue of this auction is like obviously exactly equal to the revenue of the revenue optimal auction with this n bidder. The only time it collects revenue is when it sells to one of the first n bidders if it's just running the revenue optimal auction. The only time it deviates from the revenue optimal auction, it gives the item away for free, so it doesn't make any more revenue. Okay, so this makes revenue exactly equal to the, this is an n plus one bidder auction, but it gets revenue equal to the optimal n bidder auction, but it does always allocate the item. The revenue optimal n bidder auction does not always allocate the item. This n plus one bidder auction does always allocate. And the claim is that the victory auction is obtains the maximum revenue amongst all mechanisms that always allocate the item. The reason that the revenue optimal auction is able to outcompete the victory auction is exactly because it sometimes does not allocate the item. But if we can argue that the victory auction obtains the maximum revenue amongst all mechanisms that always allocate the item, well, that means it only obtains more revenue than this dumb auction here. The one always allocates the item. And this one obtains the optimal revenue when there's n bidders. So that means the victory auction with n plus one bidders always gets more revenue than the optimal auction with n. Okay, and we already know how to prove this. Remember the upshot of this long derivation we did? It was that the expected revenue of our mechanism was equal to the expected virtual welfare of our mechanism. Right? The expected virtual value of the person we allocate the item. That was the upshot of this long derivation. So, the revenue optimal auction allocates, solves this optimization problem by giving it to the person who has the largest virtual valuation, unless it's negative, in which case it gives it to nobody. But if we need to always allocate the item, then we don't have the option of not giving it to anybody. We have to sometimes give it to someone who has a negative virtual value. But who should we give it to? Well, we should give it to the person who has the least negative virtual value. So we should always give it to the person who has the largest virtual value, whether or not it's negative. But for regular distributions, the virtual value function is monotonically the same. So giving it to the person who has the largest virtual value is just giving it to the person who has the largest value. Okay, just giving it to the person who has the largest bid. So we just recover the victory auction, the second price auction without a reserve price. Okay, the second price auction without a reserve price for n+1 bidders is revenue optimal amongst all mechanisms that must allocate the item. The only reason not revenue optimal period is because you can make money by artificially decreasing supply by sometimes not allocating it. But there's an auction that always allocates the item and gets the revenue of the revenue optimal auction with one fewer bidder. This dumb auction that just gives the item for free to bidder n+1. And so that means that maximizing welfare with n+1 bidders always makes you as much money as maximizing revenue with only n bidders, no matter what. Okay, so it's like a good reason perhaps to focus on welfare maximization over revenue maximization, to the extent that welfare maximization, but like say you're running some auction platform, to the extent that welfare maximization makes the platform even a little bit more attractive to people, right? Like if it makes it sufficiently more attractive that you recruit even a single additional user to your auction, you've already made more revenue than you would have had you devoted, the same effort to trying to squeeze the lemon a little harder and run the revenue off. Okay. Questions? I'll see you guys next time.